Okay, YouTube, in this video what we're going to be doing is using what we call the standard normal distribution in order to basically model what a population's data might look like and allow us to calculate probabilities from that. And so the standard normal distribution is a little bit different from what we would consider to be a normal distribution. In a standard normal distribution, you can see that these values down at the bottom are given by the letter Z. And this letter Z is what we refer to as a z-score, but what it does is it tells how many standard deviations above or below the mean that we lie here. So a z-score, we're going to start with this here, is the number of standard deviations above or below average a data value lies. And so you can see that with our normal distribution, if we were to take all the x values down at the bottom and change them into a statement that said you are this many standard deviations away from the origin, then you would see that the z-score at the average here is 0 because it is right directly on top of the average. When we look at these three standard deviations to the right, you notice that there's a positive 1, positive 2, positive 3. These are stating that these x values are 1, 2, and 3 standard deviations above the mean. Now you'll notice that our z-scores on the left, are -1, -2, and -3, and they certainly tell us that we are 1, 2, and 3 standard deviations away from the mean, but you'll notice that they're negative. And so one thing we want to indicate here is this: positive z-scores mean above average. And when we have negative z-scores, below average. Okay, and so what we're going to work on in this video is basically transforming all of our x values that we normally had. For instance, in our last video we had talked about excuse me, some test scores here. But basically, if we were to take all of these x values and convert them into 0, 1, 2, 3, and -1, -2, and -3, what it's going to do is make our job a little bit more convenient and a little bit easier to communicate, because then we could say, instead of x values, this is how many standard deviations above or below the mean the x values we care about lie. And so we have a formula for calculating z-scores, as a matter of fact, and that formula is this formula that we see here. And it says that the number of standard deviations above or below the mean that a given data value is given as x minus mu over sigma. And we want to rewrite this again here. It's just that I don't have a lot of room. So what I'm going to do is I'm going to flip over to this canvas here. But I want you to write next to your formula here that z is equal to x minus mu over sigma. And what we're going to do is translate this. We have the number of standard deviations, the data value lies above or below the mean. That's our z-score. What this is equal to is the data value. Let me write it this way. Our x value here, which is the data value in question here, the data value, minus the average. And this is all divided by the standard deviation. So you got to trust me on this one. What this is doing is telling us how far above or below average we are, but it's telling us in terms of a number of standard deviations that we have walked above or below the mean. And so what I want to do is kind of articulate why we would want to change things into a z-score in the first place by taking a look at this example here and setting it up kind of the same way that we had looked at in the last problem. So what we have here is that a study finds that the weights of infants at birth are normally distributed. That means that we have a bell-like distribution when we look at their data. They tell us that the mean of this birth weight of a child is 3,270 grams. So 3,270 grams. Let's go ahead and start by writing that down. Our mean is 3,270, and we're going to label this in grams. Now, they also tell us that the average spread away from this average is by give or take 600 grams here. So the question here is that if an infant is randomly chosen, okay, what is the probability that the infant weighs 4,170 grams or less? Okay, so what we're going to start by doing is start by sketching our curve here. Okay, and our curve looks like this. okay, our normal curve. And what we're assuming is that our average is in the middle here. And I'm going to start by filling in our average, 3270. This is our mu. So what we're going to do is we're going to partition our set here, giving it 3 standard deviations above and 3 standard deviations below the mean. And I'll just grab my calculator here. We're going to do this with x values first, and then what we're going to do is we're going to convert them to z-scores. So what we get is a situation where if we were to take 3270 and add on 600, we would have 3870 here. So we'd have 3870 would lie there. If we were to add on another 600, we have a 4470, and then our last one here, we would add another 600 grams on top of this, plus 600, we would get 5070. So this is down here a number of grams, okay? So we've gone 3 standard deviations above average as they've reported average and standard deviation to us. Now if we were to go 3 standard deviations below average, that is, let's start with 3270 again and take off 600, we would get 2670 here, 2670 grams here. Take off another 600 there, this would be 2070. And take off another 600 there, we get 1470. So with all of these listed out here, the question we're trying to find is what is the likelihood that our x value is less than or equal to 4,170 grams here. And so we could see that 4,170, the interesting thing is, and let me switch colors here, is that 4,170 is going to be somewhere down here. 4,100, let me rewrite that 4,170 grams is going to be down here. And so when we say how likely it is that we have a child that has a birth weight of this or less, then what we're really doing is we're describing the percentage of the population that lies over here to the left. And so what makes this difficult is that we do have an empirical rule that says, well, 34% of the population would be between here, and also here and here. We could say 13.5% of the population between here and here, 2.35% of the population here and here, and 0.15% of the population out here. But what we don't know is kind of like this mystery section over here. And so what we're going to do is essentially this. We are going to take these x values down here and we are going to convert them to z-scores. And so the neat thing about converting them to z-scores, let me do this. We'll do a z-score for our, say, 3870 first here. Our z-score formula says take that data value, 3870, and if you want to know how many standard deviations above the mean it is, which it's 1 standard deviation above the mean, what we're going to do is we're going to subtract off the mean. Our mean here is 3270. So you look, I'm just using this formula up here. Take your data value minus the mean, and we'll divide it by the standard deviation. And so what you see here is that our standard deviation being 600, we end up with 600 over 600, which basically tells us that this is 1.00 standard deviations to the right. So underneath this, I'm going to write 1. Here I'm going to write 2. Here I'm going to write 3. And underneath this, I'm going to write 0. Basically, if we were to put these through the z-score formula, it would tell us that you are 0, 1, 2, and 3 standard deviations away from this average value. And if we were to go to the left, we would say that this is -1, -2, and -3 here. So what I'm attempting to do is change all of these into z-scores, because what I can do also is actually grab a z-score for this also. So underneath our 4170, I want you to notice that we just filled all of this problem out like we did in the last problem, except for this 4170 is kind of floating in between these 2 standard deviation values. We're going to first find a z-score for 4170. So we're going to say the z-score, and this is for 4170, would be our data value, 4170, minus the average, which is 3,270, over 600. And what we'll need here, of course, is a calculator. We say 4170 minus 3270, we get 900. And so this 900 over 600 here, let's go ahead and work a decimal for this. If you put this in your calculator, we get 1.5. 900 divided by 600, we get 1.5. So 1.5, but one thing I want to indicate is underneath this x value down here, we're going to write 1.5. And so the fabulous thing about this is that we could say that really what we're trying to find is the percentage of the population that lies less than 1.5 standard deviations above the mean. So now, the reason why this is different from our first set of problems is because in our first set, we did lie on exactly on these standard deviation values, and we're able to use our empirical rule. For the second set, what we're going to have to do is rely upon what we call a standard normal distribution table to help calculate this probability. And so what I'm going to do is I'm going to show you that this standard normal distribution table right here, it looks like this. And what you're going to see around the margins here, around the outside, is you're going to see this z-score. And what the z-score is telling us, again, really is the number of standard deviations away from the mean in which we lie. And so what you'll notice here is on the left, we have z-score starting at 0.0, 0.1, 0.2, 0.3, 0.4. This is telling us that we're going over the average by this many standard deviations. Our z-score goes all the way up to 3.0. Okay? In other words, we usually only go about 3 standard deviations to the right. Now, another thing about this table, let me pull that back open again here, is that you have a top margin, and you'll see in the top margin that these go out to the nearest hundredth of a value here. So in other words, if we wanted to do something for like 3.09, what we would have to do is first of all go to 3.0 and then trace our way over. We'd have 3.00, 3.01, 3.02, 3.03, 3.04, all the way out to 3.09. The furthest right this is going to go is 3.9 standard deviations. Now you're going to notice this little sketch down here on the bottom right corner. But what this table is actually telling us is it's telling us the area under the curve between the average and the number of standard deviations to the right of the mean that we've gone. So in other words, if we wanted to find this right here, this area, one way we could interpret this is, well, if our table is going to tell us the area under the curve between the average and a certain number of standard deviations to the right, what we could do is we could just look up that number of standard deviations on our table, and what it should do is give us the area under the curve between the average and this number of standard deviations out on the right. So looking at this, we're going to find a z-score of 1.50. So starting over here on the left, we would say 1.0 is right here, 1.1, 1.2, 1.3, 1.4, 1.5, and we want 1.50. So 1.50 would be the first little spot to the right here, but we'd say 43.32% of the population lies between here and here. So you'll notice that they give us 4 decimal places here, which is appropriate. We say 43.32. What could we also say about the left side of this distribution in terms of how much area is underneath it? Because what we wanted to do was find all of this red area. Keep in mind that the left side of this distribution contains 50% of the data, as does the entire right side. So the probability that we randomly have an infant born that is weighing less than 4,170 grams would be the same thing we get if we were to add up all the area under the curve here, which would be our 50% plus 43.32%. So this area over here, what we're going to say is 50% plus 0.4332. What we end up with is 0.9332. And looking at our distribution here, we could say that this makes reasonable sense that our area would lying to the left of 1.5 standard deviations would be so much because you've already got a lot of the population here, especially around the middle. So what I want to do is I want to take another stab at this here, and we'll just change up the probability that we're trying to find. And what I would like to do also is try to streamline this effort. So when it comes to using z-scores in this table to calculate things here, you'll notice that I've got this down to a few steps here. Number one is going to be sketch the bell-shaped curve, place a midline for the average x value, and then make 3 partitions on either side of the average to indicate our standard deviations to the right and left. Next, what we'll do is label the x values which are included in the probability that we desire to find, and shade the portion of the curve that represents our probability. So just like we did last time, because we're using the same data set here, we would say we have the same curve. I'll try to give myself some space here. We'd say here's our normal distribution. And in the middle of this normal distribution here, we had in grams 3,270 grams. So now looking at this, we would say 3 standard deviations to the right and 3 standard deviations to the left. We fill in all of our x values here, which we had 1470. We also had 2070. We also have 2670. Now going up by 600s, we had 3870. Here we have 4470, and here we have 5070. So now that we've drawn out our bell-shaped curve and drawn our 3 partitions to the right and left and labeled our x values here, the next step on the docket is essentially this: to determine where the probability is that we're trying to find here. So they say that, of course, A study finds that the weights of infants at birth are normally distributed with an average of 3,270 grams. So here's our average. And a standard deviation of 600 grams. It says an infant is randomly chosen. What is the probability that the infant weighs less than 2,790 grams? So you can see that 2,790 grams. The thing here is this. It's going to lie somewhere in here. We say 2,790. And so if we were to sketch in and shade the part of the curve we want here, we're asking how likely is it that our infant randomly chosen here has a weight or an x value that is less than or equal to, greater than or equal to, we're talking about at least 2,790 grams. We want to know how likely it is that our x value is randomly to the right of this here. So what we're going to do is we're going to use our table that I've provided us with here to go figure this out. The only problem is that this table here requires us to use z-scores, or a number of standard deviations above or below the average. So the neat part about this is if you've already written out then these values here, the average and the standard deviations, we know their z-scores are 0, 1, 2, and 3. We have over here -1, -2, and -3. And so in terms of the steps that we're going to take to solve this, once we've got this all sketched out and shaded, basically step 3 is going to say convert any x values into a z-score to indicate how many standard deviations away from the mean the x values lie. You can see that all of these values in red have already been converted. When it comes down to converting 2,790 into a z-score, what we're going to see is that it's less than 0, but it's greater than -1, maybe like -0.5. What we're going to need to do though is figure this out. So we say our z-score for 2790. Start with this. 2790 is our value, our x value. We're going to subtract off the average, which is 3270, and we're going to divide by the value of sigma, our standard deviation, which is 600. So when we subtract these here, we actually get -300 on top over 600, which comes out as a decimal. We always want to write this as a decimal out to 2 places of this. And so I'm going to write underneath this here that basically this has a z-score of -0.5, which means that really it's a half a standard deviation to the left. Now the interesting thing about this table is, and I'll try to put this side by side here, remember that this table, according to what we have written down here, only tells us the area under the curve between 0 and the number of standard deviations that are to the right of the average. So when we look at this picture here, basically what we're going to do is we're going to split this up into 2 sections. We're going to say, well, we need all of this stuff on the right here, which is absolutely 50%. So we're definitely going to get 50% that we're going to have to add on. Now the other part we need is this little sliver right here. And because we know that this is a half a standard deviation away but to the left, but also because we know that this curve is symmetrical, and so if we were to go a half a standard deviation to the right, it'd be the same thing, we're going to look it up in this table as if this were a positive 0.50. So to ask this table basically how much area under the curve is there between 0 and -0.5, it'd be the same thing as asking between 0 and +0.5. We'll find 0.5 on our table here and go to 0.50, we see 0.1915. So I'm going to make a little note here that inside this little sliver here between -0.5 a standard deviation and the average, which is 0 standard deviations, we have 0.1915. So we're going to add this to I'll try to squeeze this in here, 1915, and adding these together what we get is 0.6915, or the likelihood that this happens is about 69.15%. So what I want to have you try is, again, with the same example, find me what is the likelihood that the infant weighs more than 3,990 grams, which would lie somewhere over here on the right of this distribution. When you're ready to take a look at this, go ahead and unpause your video. So for part A, if we were to sketch this out here, of course I'm going to try to get this whole sketch rocking again here. Step 1 is basically get your sketch out, and let's put on our average x value, which in this case in grams was 3270, and we'll go 3 standard deviations above or below the mean. Okay, so we have 3 above and 3 below. And so what we're going to say here is that we have 2670, we have 2070, 2070, and 1470. And on the right side here we had 3870. Here we have 4470, and then over here we have 5070, and this is all in grams. So when we want to answer this question, what is the likelihood or the probability that an infant weighs 3990 grams or more, we're going to say that our infant's weight, x, is greater than or equal to 3990. And so now that we've got these on here, let's go ahead and shade the portion we want to find. Now 3990. 3990, what I know is it's going to be somewhere right here. 3990. I'm going to draw a little mark, and I'm going to draw a little vertical line up here, and we want to know how likely it is that it's greater than, okay, weighs more than this. We'd say that this is the portion of the curve we want to find, or the area of the curve. So we can see that it's definitely less than 50%. Basically what we're going to do now is just convert everything over to z-scores. So we have 0 standard deviations away from the mean, 1 to the left, 2 to the left, 3 to the left here. As we go to the right, we would say that this 3870 is 1 to the right, or 4470 is 2 to the right, and 5070 is 3 to the right of the mean. What we're going to want to get is a z-score for 3990. So to find a z-score for this, we say z. It would be our data value, 3990, minus the average, which was 3270, and we'll divide by the number or the size of the standard deviation here. So getting our calculator out here, we have 3990 minus 3270 comes out to be 720, okay? And then we have divided by 600 here, 1.2. So in other words, what we could say is that this is 1.2 standard deviations to the right of the mean. So now what you have to understand is that we're going to look this area up in the table, but we're going to have to pull a little magic here, because the reason why is because remember that when you look up a z-score in this table, like 1.2, what it's going to tell you is the area under the curve that is between the average, and that number of standard deviations to the right. So when we look up 1.2, that's easy enough to do. We'd say a z-score is 1, 1.1, 1.2, and we say 1.20 would be 0.3849. What we're being told is that this is 0.3849 in here. So to find this probability here, what we're going to have to do is we're going to have to use this plan of saying that because we know everything to the right of this is 0.5000, and because we know we don't want this right here, we want the leftover, what we're going to do is we're going to take 50% of our distribution here, and we're going to subtract off the 0.3849 that we don't want in this. And what that's going to do is it's going to give us 0.5 minus 0.3849. It's going to give us the remaining 11.51% that lies out here. So our probability here that we randomly grab a child that was born greater than 3990 is not very good. It's only 0.1151. So for the last part of this, you should have answered why it makes sense that the probability that our z-score is less than or equal to 0. What we're really saying is this: how likely is it that we grab something that is 0 standard deviations away from the mean or less? And so in other words, what we're grabbing here is everything to the left of the average, basically from 0 standard deviations to the left. To randomly grab a z-score out there is really to say randomly grabbing a person in the population that's below average. And so half of the population lies below the average, and so therefore we would have to get 50% there. Cheers.